Welcome to this explainer. Today we're going to completely redefine how you understand reality itself. Seriously, we are moving way beyond that old sci-fi cliché of quantum entanglement being some kind of spooky action at a distance. Instead, we're going to pop the hood of the universe and look directly at the underlying architecture of existence. If you've ever stopped and wondered whether the world you see is actually what's really there, well, buckle up. We're exploring the incredibly radical idea that the universe you and I experience every day is, at its core, fundamentally compressed.
You know, even Albert Einstein famously struggled with this. He's the one who coined the phrase spooky action at a distance, mainly because standard quantum mechanics tells us that two particles, which could be separated by light years, can instantaneously coordinate their states. Einstein absolutely hated this idea. It completely defied his universal speed limit, the speed of light. Nothing should communicate faster than that, right? But what if these particles aren't actually communicating across vast stretches of space at all? What if the actual distance between them is the illusion?
Okay, let's dive into this by looking at something completely different. A fascinating, kind of catastrophic failure happening right beneath our screens on the internet right now. It's called semantic collapse. Basically, semantic collapse happens when a system just degrades because it's forced to process way too much synthetic noise or heavily compressed data. It gets overwhelmed, breaks down, and literally starts hallucinating. Now, I know that sounds completely unrelated to quantum physics, but this mathematical failure happening inside our computer chips turns out to be the absolute perfect metaphor for human observation. What if our own brains are glitching out in the exact same way when we look at the universe?
To understand this, look at modern AI hardware. It relies heavily on things called FPU gamblers to guess at math. Imagine a slice of Swiss cheese. To process data at blistering speeds, these chips just chop off tiny fractions of numbers, leaving holes in the data. They literally guess the missing parts to save time. This creates a lossy, degraded projection where the exact data paths are just gone. On the flip side, you have exact deterministic hardware, like ALU surveyors. These function like perfectly interlocking, exact gears, calculating absolute, uncompromising truth with zero shortcuts. Our source material poses a really radical question here. Just like AI uses that Swiss cheese method to create a lossy projection, could human observation be doing the exact same thing to the underlying exact math of the universe?
Let's start breaking this down in Section 1, the quantum gambler and Q-number reality.
We'll kick things off with the probabilistic view of the universe. This view acts exactly like that ultimate FPU gambler guessing the missing pieces of cheese. Championed heavily by physicist Vlatko Vedral, this argument basically says that classical reality, that comfortable idea of little solid particles bumping around like billiard balls, is a total illusion. Particles aren't fundamental at all. Instead, reality is constructed of Q numbers. Think about standard numbers for a second. It's like putting on your socks and then your shoes. 3 times 5 is the exact same as 5 times 3, right? The order doesn't change the outcome. But Q numbers are these complex tables of probabilities where the order of multiplication fundamentally matters. It's like trying to put your shoes on before your socks. The sequence actually changes reality. That little mathematical quirk is the hidden engine driving Heisenberg's famous uncertainty principle.
And in Vedral's view, observing a system doesn't destroy it or collapse it like you're popping a balloon with a pin. Instead, the observer simply becomes entangled probabilistically with those Q numbers. You're literally linking up with the math. This creates a constantly branching probabilistic reality. What's really brilliant about this is how it completely replaces the need to view human consciousness as some special mystical force that dictates reality. You aren't magically collapsing the universe with your mind. Your particles are just dancing and correlating with its particles. You're just one quantum system mingling with another quantum system in a giant web of probabilities.
Which brings us to Section 2, the deterministic substrate.
So what if we zoom in even further? What if the substrate of the universe isn't a probabilistic casino full of guessing games, but something entirely exact? Theoretical physicist Gerard 't Hooft offers a massive counterpoint to the probabilistic view. Imagine the universe not as a fuzzy cloud of chance, but as an impossibly complex, perfectly exact chessboard. In this framework, foundational reality is actually a deterministic cellular automaton. It acts as a discrete tensor network, a perfectly exact, uncompressed geometric lattice where absolutely everything happens for a strict, mathematically absolute reason. No gambling allowed.
To make this uncompressed chessboard work, this deterministic substrate actually splits reality into two distinct layers. Way down at the Planck scale, the absolute bottom of reality, you have fast variables. These are microscopic, wildly fluctuating vacuum states. Now, imagine trying to take a photograph of a Formula One car zooming by, but you're using a really slow camera. You don't get a crisp image of the car, right? You just get a massive, smeared blur.
The fast variables are that exact F1 car, but because they move so fast, human observers can only interact with the slow variables, the blur. That blur is what we perceive as macroscopic physical objects. So in this view, quantum mechanics isn't the fundamental truth of the universe. It's just an emergent statistical tool, a blurry photograph of incredibly fast, exact, deterministic behavior that our human brains simply do not have the bandwidth to see clearly. Now, let's tie these together in Section 3, Topological Aliasing Explained.
This is where those probabilistic Q numbers and that deterministic exact substrate violently collide. And here is the ultimate twist. Entangled particles aren't two separate magical objects communicating telepathically across the galaxy. They are the exact same informational node in that deterministic tensor network. Let me say that again because it's a real game changer. They are the exact same point of information. Because we, the human observers, have a finite bandwidth limit, we can't process the true higher dimensional geometry of the universe, so that single node gets projected into our 3D reality twice. This phenomenon is known as topological aliasing.
Imagine a single perfect point of data existing in a higher dimension. Because our brains have a hard physical limit on what they can process, what we call our Shannon capacity, we create a massive informational bottleneck. Our brains act exactly like that lossy zip file or that Swiss cheese computer chip we talked about earlier. We essentially try to unzip that single high-dimensional point, but our flawed, limited 3D brains literally can't handle the math. As a result, it gets rendered and projected as two completely distinct, separated particles in our macroscopic reality. The separation isn't real. It's an artifact of our own mental hardware.
Just think about the sheer weight of this concept for a second. Macroscopic separation is a thermodynamic rendering error. It's an illusion. It is literally an aliasing fold caused by our own limited observation capacity. The whole idea of spooky action at a distance completely vanishes when you realize those two entangled particles were never actually separated in the underlying math to begin with. They look incredibly far apart to us, but in the source code of the universe, they're occupying the exact same pixel.
Which leads us perfectly into Section 4, the topological severance limit.
Okay, so if this is all just a human capacity limit, what happens when we overload it? Just like your home Wi-Fi completely crashes if 10 people try to stream 4K video at the exact same time, reality has a mathematical breaking point too. This brings us to the topological severance limit. This is the exact moment where the sheer structural density of a localized network strictly exceeds our macroscopic boundary limit to observe it. When the sheer amount of information becomes too massive for our limited capacity to handle, the conditional independence that holds our rendered reality together just fails and entanglement permanently snaps.
Standard quantum mechanics usually blames this breakdown of entanglement, a process called decoherence, on random thermal noise or environmental leaks messing with the system. But this framework dictates something entirely different, and frankly, I think it's much more elegant. It dictates that entanglement severs deterministically simply because our human hard drives run completely out of space to render the connection. The informational topology physically saturates. Reality decoheres purely because of the capacity trace of the observer. We don't break the system with noise. We literally just run out of RAM to see it.
Let's look at the big picture in Section 5, the lossy hologram.
So what does this massive paradigm shift actually mean for the continuous 4D reality you and I wake up to every single day? Well, it means that everything we experience is basically an epistemic artifact, an illusion created by our own limits. Continuous spacetime is really just statistical data pulled back into a simplified geometry our brains can handle. And what about things like rest mass and gravity? Think of them as physical friction. They're merely the entropic residue, the leftover glitches and exhaust from our brains constantly compressing higher-dimensional, exact truth into a lossy 3D format. Under this model, even the Big Bang wasn't a dynamic physical explosion in time, it was simply the topological saturation point. It's the absolute maximum limit of what our capacity can possibly render looking backward. And black holes? They represent the maximal limit of our capacity to observe anything at all.
The implications of this are absolutely staggering, right? It reshapes physics from the ground up. I want to leave you with this final, profound thought to ponder today. If everything we see around us is just a lossy zip file because of our limited biological hardware, as we finally evolve from probabilistic guessers to exact deterministic surveyors, what happens when we finally build a machine that has the capacity to see the universe completely unzipped? Thank you so much for joining me on this explainer. Keep learning, keep questioning the systems around you, and I'll catch you next time.